In this video, we're going to walk through the basics of positional numbering systems. These are the types of numbering systems used for most of the numeric data that we have on our computers. Now, to begin with, we're going to start with a decimal number because we all understand decimal. So I'm going to choose 1034. Now, you may or may not be amazed that I could write this sequence of digits and come to the conclusion that it's 1034. But we've had a lot of experience with decimal numbers growing up, and we may have forgotten the basics of how they're constructed. So I want to point out that this literally says a 1 in the thousandths place. There's a 0 in the hundreds place, a 3 in the tens place, and a 4 in the ones place. So the way we construct this then, the number 1034 from this series of digits, is really that we've got 1 1000s. So we have 1 times 1000. To that we're going to add 3 tens, so 3 times 10. And to that we're going to add 4 ones. Right? Now, if we apply the multiplications here, we'll get 1000 plus 30 plus 4. Now, I realize there's a bit of chicken and egg here since I'm trying to show us how we constructed this, and now I have a multi-digit number or two. But this is just to remind you of how these numbers work. So when I write 1034, I really am indicating that the right digit here, especially in absence of a decimal point, the right digit here is in the ones position, and every consecutive digit to the left of that is in the next highest position decimally. So we go from ones to tens to hundreds to thousands to 10,000s and so on. And then each of those digits is a coefficient that's multiplied by the value of that particular position. So we have 1034, literally. Right? Now, to make this a little more refined so that we see what's going on, once we recognize that as we go from the rightmost position to the decimal place, which we would imagine would be right here, and every time we come to the left, we increase our power of 10, we can sort of generalize this all out. And this is the way it works for all bases, not just decimal, but binary and hexadecimal and other bases that we'll talk about, and other arbitrary bases we could imagine. So the way we do this is we can rewrite this in something called the coefficient base exponent form. So I'm going to take this number and rewrite it in that fashion. Let me clear this up just a little. And what we'll notice here is that this was worth 1, but that's really 10 to the 0th power. This position is 3 in the coefficient, but it's 3 times 10s. So that's 10, which is the decimal base, to the first power. The next one is 0 hundreds. So this position is worth, oops, just writing 100. This position is worth 10 squared. This position is worth 10 to the third power, 10 to the third being 1000. Right? So it's 1 times 1000. So if we convert this number to its coefficient base exponent form, we'll get 1 times 10 to the third plus, now I'm not even going to bother writing a term for 0 coefficients because the result of 0 times anything is 0. So we just skip those altogether. But this will be 3 times 10 to the first plus the coefficient 4 times 10 to the 0th power. And if we actually applied each of these exponents, we'd see that we have the equation that we started with before. So this generalizes to arbitrary bases. And even better, when we go to other bases, we're going to see one more pattern. And that's, if you look up here, the powers go up by 1 as you move to the left. So here's to the 0th power. The rightmost position, the one next to the decimal place, is always going to be the 0th power. And anything to the 0th power will always give you a 1. So that's always the ones position, no matter whether your base is 17, 2, 10, or 23. As we move to the left, each digit position, the exponent increases by 1. So if we go from the exponent of 0 to 1 to 2 to 3. And the opposite is true going the other direction. We always go down. And as such, we name each of these positions, or at least very frequently in computer science, we'll talk about a particular digit or bit by its position number. And so we would call this thing in the 0th position. This is in the 1st, 2nd, and 3rd position because of the fact that those position numbers are equivalent to the exponents of the base that they represent. Okay? So we can also do this in totally arbitrary other bases. So let's say we want to do something in binary. Now, you should have been introduced to binary in the past, so we're just going to stick with some basics of this for the moment and just say that in binary, we are really talking about a base of 2. So all the positions in a binary number are going to contain coefficients multiplied by our base, which will be 2, to some exponent. So the base will be raised to an exponent of 4th multiplied by the coefficient. So I might write a number down like 1, 0, 1, 1, 0. And this is in binary. And make it clear that this isn't decimal. For the moment, I'm going to write a subscript of 2. However, for all practical purposes, you're going to see me writing 1s and 0s in the future where I don't write a base 2. And it should be clear by circumstance that I indicate, or that I mean that this is a binary number. There are, of course, decimal numbers, as well as numbers in other bases, that are constructed only of 1s and 0s, and I'll try to be sure whenever one of those comes up that I'm very clear that that's a decimal number or otherwise. Okay? So here's our binary number, 1, 0, 1, 1, 0. And what I want to do is write this in coefficient base exponent form, the complete one, skipping again any positions with a coefficient of 0. So first I'll mark the position numbers because that's going to be equivalent to the exponent. So this is position 0, 1, 2, 3, and 4. And just for kicks, that means we're going to have 2 to the 0th power here, so this position is going to be worth 1 multiplied by its coefficient. This position will be 2 to the 1st power, and so that's going to be 2. 2 to the 2nd power is 4, 2 to the 3rd power is 8, and 2 to the 4th power is 16. Now I don't have to actually think all the way through what is 2 to the 3rd power, what is 2 to the 5th power, that kind of thing. If I'm documenting the value of each of these positions, I can just start with 1 on the right because the 0th position will always be worth 1. And then for every position to the left, I just multiply by the base. So here in base 2, I said this position is worth 1, this is worth 2, 4, 8, 16. We're just multiplying by 2 each step. We'll do this again in another base in just a minute. All right, so the coefficient base exponent form for this particular binary number then is going to be a coefficient of 1 multiplied by the base, which is 2, raised to this position's exponent, so 2 to the 4th, plus coefficient of 0 we'll skip. Here's a coefficient of 1 in position 2, so that's 1 times the base raised to the position number 2. Plus, here's another coefficient of 1, 1 times the base 2 to the position numbered power, 1. And then we won't bother adding the value of the position with the coefficient 0 there at the end. And so this is the complete coefficient base exponent form of this number here. And if, of course, we wanted to take this all the way and figure out what its decimal equivalent was, since here we are thinking in decimal rather than binary, it's pretty easy for us to do. So this 2 to the 4th is really 16. This 2 squared is really 4. And this 2 to the 1st is really 2. So we have 16 plus 4 plus 2. And this is one of the great advantages of binary when we're doing this kind of thing. Remember before when we had things like, oh, it might be 7 times whatever here and there. In base 10 in decimal, this isn't so bad. But if we were doing something in base, say, 13, and I had a coefficient of 3 times some power of 13, it would not be so easy to figure out what those are. But since each of these will always have a coefficient of 1, it's almost as if the coefficients don't exist because they don't change anything, basic identity, right? So 16 plus 4 is 20, plus 2 is 22. So 10110 is the same thing as 22 in decimal. Now let's go to another base. This time we'll look at something just up. We'll do base 3. So with base 3, every position is going to have a value that is worth 3 raised to some particular power. So I don't know, we'll just write down some number here in base 3. Now in base 3, well I should say in base 2, binary, we know all the digits are going to be zeros or ones. And in base 10, we know all the digits are going to be 0 through 9. But we don't necessarily know what the digits are going to be in base 3, or at least we may not at this point in our lives. But we can figure this out pretty easy. It turns out that whatever base we pick, and I'm going to switch out for just a second here. Let's say we pick base k. Whatever base that is, of course it's an integer and it's a number that's 2 or higher for sure, but whatever base this is, we're going to be writing down a bunch of terms where inside the parentheses there's our base k, and then we're going to raise something to some exponent, right? So up here there's some exponent that we raise things to based on the position. Then we have the coefficient here. The coefficient will be c. Now in base k, the coefficients can go anywhere from 0 all the way up to and including our base k minus 1. So we can feel that out with the two bases that we're somewhat familiar with. The first being decimals, so that's base 10. In base 10, all the digits that we write are 0 all the way up. Let me do the same notation. 0 all the way up to 9. In base 2, binary, we write from 0 all the way up to the base 2 minus 1, which is 1. So 9 is 10 minus 1. 1 is 2 minus 1. So whenever we pick some new arbitrary base, k, remember that our coefficients will be the integers from 0 up to and including the base minus 1. All right, so let's do a base 3 number. Base 3, which means our coefficients are going to be within that range of 0 all the way up to 2, right? Because 2 is 3 minus 1. So we'll just write some arbitrary number. That means each digit is 0, 1, or 2. 2, 0, 1, 2. Base 3. Just to ensure that we don't confuse ourselves that this is 2012 in decimal. Right? Probably any time I'm using an unusual base, I'll identify the base with a subscript at the end of the number. Okay, so what is this? Each position here is the 0th, 1st, 2nd, and 3rd, as always. So what are their values? So this will be, this is, I'll mark the positions again. This is the position 0, 1, 2, and 3. then we have these values for each position. That'll be the base 3 raised to each of these powers. So 3 to the 0 will be 3. 3 to the first will, wait a minute, 3 to the 0 is not 3. 3 to the 0 is 1. Anything to the 0 is 1. All right. So 3 to the first power then is 3. Woo! Mental math killing me here. 3 to the second power is going to be 9, which is the same thing as 3 times 3. The next position would be 27, and if we had another position, 27 times 3, that would be worth 81. Right? Okay, so we have this value here. We can write it out in its coefficient base exponent form. So this is going to be the coefficient of 2 multiplied by 3 to the third power plus, skipping the 0, this guy right here, a 1 times 3 to the first. 1 times 3 to the first plus 2 times 3 to the 0. Right. And we could take that further to figure out its decimal equivalent by just applying everything here. So for this value, this is really 2 times 27 plus 1 times 3. Well, I'll write it out. 1 times 3 plus 2 times 1. So this is really 2. This is really 3, so we have 5 altogether. And then this one is, what do we have here? 54. So 54 plus 5 is 59. So 2012 base 3 is the equivalent to 59 hexadecimal. And that's the basics of positional numbers. Now, there's one layer deeper that I want to go to before we end this particular video, and that's to look at what happens not just by increasing these position numbers as we go to the left, but decreasing the position numbers as we go to the right. So let's do this by looking at a base we're very familiar with. That'll be base 10 decimal. And in base 10, recall that all the coefficients go from 0 to 9. Now, if I write some number here, let's do, let's go off the one we had before, 1034. But this time I'm going to add a decimal point and then 2, 5 after it. Okay. Now, there are some parts of this that we already definitely understand and have reviewed. So the positions that I'm marking in red for this digit, this is the 0th position because it's the rightmost digit before or to the left of the decimal point. And as we go to the left, each position goes up by 1 very easily. Right? Now that means as I go to the right, each position goes down from 3 to 2, 2 to 1, and 1 to 0. So if I go one more, that should go down by 1. So this must be the negative 1th position, and this must be the negative 2's position. So what does that mean in terms of exponents? Well, for the stuff on the left of the decimal point, right, this is not hard. This is 2 to the 0th power, which we know to be 1. 2. This is decimal. 10 to the 0th power, which is also 1. 10 to the first power, which is 10. 10 to the second power, which is 100, and 10 to the third power, which is 1,000. Over here, we're going to have two more unusual things. We'll have 10 to the negative first and 10 to the negative second power. So what does that mean? 10 to the negative first. If you remember your laws of exponents, whenever we have a negative exponent, that's the equivalent to the inverse with the positive exponent. So this is the same thing as 1 over 10 to the first, which is the same thing as 1 over 10, which means this is the 1's position, this is the 10's position, and this is the 1/10th's position, or the 10th position. So it tells us how many tenths there are. In this case, 2/10. For the next position, where the 5 is, that position is worth 10 to the negative second power. So we apply the rule of negative exponents, and that means we have 1 over 10 squared, which is the same thing as 1 over 100. So this is the 100th position, just as we learned in grade school. So now we have 1,034 and 2/10 plus 5/100. Well, we don't like to say that, and we don't normally like to deal with mixed fractions in that way. And so we would try to find a common denominator to speak it out loud, just like we try to find common denominators with our fractions when we're working with them in equations. So the easiest common denominator between 10 and 100 is to take the 2/10 all the way up to 20/100. And so this becomes 25/100. So 1,034 and 25/100. Now let's switch bases again and do this one more time in binary. All right. So our base is 2. We are in binary. Our number will be 10011 point. Now this is not really a decimal point. And I don't think anyone would call it a binary point either. But it's okay if you refer to this periodically as the decimal point. Truth be told, we should generally say that this is the radix point. And really the base, too, is also the radix. They're sort of just equivalent terms. Right? But you will definitely hear me call this the decimal point from time to time. Please forgive me, but understand that it doesn't mean we're in the decimal numbering system. So 1011 point, I don't know, let's see, 01. There we go, that's a binary number, as long as we know that we're in binary. So we got to do the same thing that we did last time. Let's start with the positions. This one is the 0th, 1st, 2nd, 3rd, and 4th. But that means going to the right, we go down from 0 to -1 and say -2, just like in our decimal example. That means from the perspective of each position's value, we are looking at 2 to the 0th, 2 to the 1st, 2 squared, 2 to the 3rd, and 2 to the 4th for these. It's a horrible 4. Horrible. That's a better 4. To the right of the radix point, however, we're looking at 2 to the -1st and 2 to the -2nd power. 2 to the -1st is the same thing as 1 over 2 to the 1st, which is the same thing as 1 over 2, or 1/2. 2 to the -2nd is equal to 1 over 2 to the 2nd, which is equal to 1 over 4, which is the 4ths. So this is the halves position. This is the 4ths position. And when we want to say this number out loud, I guess if we wanted to figure out what its value is here on the right, we really have a standalone number by itself. If you think about this is a 2-digit binary number, this is the binary number for 1, 0, and 1. But it goes all the way down into the 4th position, so it's effectively telling us that there's 1/4, which by coincidence is equivalent to the 0.25 that we saw in the decimal number that we had before.